Norm to linear space. Now today we discuss about metric space. Also recall that portion. We also discuss non-linear space. So we start from definition of metric space. Okay. Let X be a non-empty set and D be a function from X cross X to 0 infinity. Okay. 0 plus infinity. Okay. X cross X to 0 plus infinity, satisfying those properties. Satisfying first one, dxy greater than equal to 0 for all xy belongs to x. Number 2, dxy equal to 0 implies by x equal to y. Number 3, dxy less than equal to d of xz plus d of zy. Okay, for all x y z belongs to x. And number 4, dxy equal to dyx. Okay, dyx for all xy belongs to x. Okay, then the structure xd we call, then the structure xd be called a metric space. Okay, and D be a metric on set X. D be a metric on a set X. Okay, now we also discuss about this one is the definition of metric space. Okay, now we also going to discuss about limit of a sequence. Also erase that portion and going to further discussion of that. Too easy portion also discuss, but this one is, let me recall that portion. Okay, limit of a sequence. Okay, limit of a sequence. Let xd be a metric space and xn be a sequence in x. Then we say that xn converges to, then we say that xn converges to an element, x converges to an element, x belongs to x if for each epsilon greater than 0, for each epsilon greater than 0, there exists n0 equal to n0 epsilon belongs to n, such that t of xnx less than epsilon. Okay, for all n greater than equal to n0, and that is limit t of xnx and tending to infinity equal to 0. Okay, now we also discuss obviously Cauchy sequence. Okay, we erase that portion and going to further discussion of that. Okay, Cauchy sequence. Let XD be a matrix space and Xn be a Cauchy sequence in X. Let XD be a matrix space and Xn be a Cauchy sequence in X. Okay. If for each epsilon greater than 0, if for each epsilon greater than 0, there exists n0 belongs to n such that d of xn less than epsilon for all mn greater than equal to n0. Okay, or d of xn plus p less than epsilon for all n greater than equal to n0. Okay, and p belongs to n. Then what we get? This implies that summation n equal to 1 to infinity d of xn plus 1. Okay, d of xn plus 1 less than plus infinity. Okay, again this implies that limit m tending to infinity d of xn equal to 0. Okay, and limit n tending to infinity d of xn plus p equal to 0. Then also known about this one, Cauchy sequence. Okay, in any one condition satisfied, then we'll talk about this one, be a xn, be a Cauchy sequence in X. Okay, now it is that portion. I'm going to further discussion of that. Now we write here complete matrix space. Okay, complete matrix space. Let XD be a matrix space. Let XD be a matrix space. Let XD be a matrix space and XD be complete. XD be complete. Okay, if every Cauchy sequence, in X converges in X, every Cauchy sequence in X converges in X. Okay, now we'll also discuss about that matrix spaces which are complete or not. Okay, matrix spaces which are complete or not. Okay, first let xy belongs to x equal to 0 1. Okay, and dxy equal to mod of x difference y. Then clearly xd be a matrix space, and let xn equal to 1 difference 1 by n. Okay, This implies that xn converges to 1 as n tending to infinity. Okay, then xn be a Cauchy sequence. Then xn be a Cauchy sequence. Okay, but 1 does not belong to x. But 1 does not belong to x. Hence xdb incomplete. Hence xdb incomplete. Okay. Hence xdb incomplete. Next, we also discuss about that. That means some sequence which is incomplete. Okay, we also discuss about that. Now we erase that portion and going to discussion about vector space or linear space. Okay, we also known about it. Vector space or linear space. Or linear space. Let X be a non-empty set. Let X be a non-empty set. Okay, and this operator x cross x to x be arbitrary operator such that be an arbitrary operator such that x plus be an abelian group. And let K be a field. Let K be a field and distorted K cross x to x. Okay, be a function satisfying be a function satisfying first one mu of x plus y equal to mu x plus mu y for all xy belongs to x and mu belongs to k. Number 2, mu plus lambda x equal to mu x plus lambda x for all x belongs to x and mu lambda belongs to k. Number 3, mu of lambda x equal to mu lambda x. Okay, for all x belongs to x and mu lambda belongs to k. Number 4, 1 dot x equal to x. Okay, then the structure is called vector space or linear space over the field K. Then the structure x plus dot is called a vector space or linear space over the field K. A vector space or linear space over the field K. Okay. Now we also discuss some further example or example of some vector space. Okay, we just write this definition of vector space or linear space. Here let X be a non-empty set and this addition operator and multiplication operator are defined in this way and satisfying some property x plus x addition operator be an abelian group and x and multiplication operator obviously satisfying certain property, then this structure is called a vector space or linear space over the field K. Okay, now we discuss about another portion. So it is that portion and going to further discussion about something. Let R infinity equal to this one. Okay, x1, x2, xn be an infinite dimension. x1, x2 dot 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 xn be an infinite dimension. Okay, now if x2 x be an operator, if x to x be an operator, that means one vector space to another vector space be an operator, and if x to k some field be a function. Okay, that means some vector space to vector space, this one be an operator, and some vector space to some field, this one be an functional. Okay, next we discuss about example of vector space, finite dimensional vector space. Okay, here we write finite dimensional vector space, finite dimensional vector space. Okay, let x equal to Rn. Okay, be a vector space, be a vector space over the field R, over the field R, and x equal to c to the power n be a vector space, be a vector space over the field C, over the field C. Okay, now we're also going to discussion about some sequence space. That means infinite dimensional vector space. Okay, we write now infinite dimensional vector space, infinite dimensional vector space. Okay, also discuss this portion, infinite dimensional vector space. Okay, especially this one is sequence space, especially this one be sequence space. Let X be the collection of bounded sequence of complex number. Let X be the collection of bounded sequence of complex numbers, and it is denoted by L infinity or L infinity n. Okay, then or thus L infinity n equal to those x equal to xn belongs to C such that xn is bounded. Okay. L infinity n xn is bounded. Now we also going to some another discussion or erase that portion and going to some discussion about that. Now x be a set, okay, then binary operation, that means this one, this be a binary operation, okay, plus x cross x to x, okay, then x plus be an abelian group, okay, and k be a field, and let k be a field. Then another binary operation, this one, dot k cross x to x, okay, be an operation or binary operation, okay, then x, this one, dot be a vector space, okay, over the field k. This one is too easy, okay, we are in vector space over the field k. Now we also discuss this subspace. Oh, that is visible or not? I think visible, okay. Now we discuss about subspace. Let x plus dot be a linear space over the field k. Let x plus dot be a linear space over the field k. Okay, then is set y subset of x is said to be linear subspace of x, if first one, x plus y belongs to this y, for all x y belongs to this y. Then we also known about that this one is subspace, okay. Now we also discuss some subspace here. some finite dimension subspace and obviously some space. Okay, we'll erase that portion and going to also discussion about that in a way. Okay, what we write here, x equal to r to the power n. Okay, then x equal to x1 x2 dot 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 xn, y equal to y1 y2 dot 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 yn. Okay, then x plus y equal to, then x plus y equal to x1 y1 x2 y2 dot 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 xn yn. Okay, hence x plus V an abelian group, V an abelian group, and for lambda belongs to K, x equal to x1 x2 dot 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 xn, okay, belongs to x, then lambda x equal to lambda x1 lambda x2 dot 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 lambda xn. Okay, then what happened? Then we show that all the assumptions of linear space hold. Okay, so Rn plus dot be a linear space over K. Okay, be a linear space over K. Now we also discuss about that there is no subset of R which is subspace, since alpha x does not belong to Y for some alpha belongs to R. Okay, here we note this one. This one is important for all. There is no subset of R to the power n which is subspace. Okay, which is subspace. Why? Since alpha x does not belong to Y. Okay, alpha x does not belong to this, that means Y, or this no subset Y such that Y subset of Rn. Okay, and x belongs to Y. Alpha belongs to R. Okay, and then we also, since for alpha belongs to R or for some alpha belongs to R. Okay, we also seen some sequence spaces. Okay, but now also known about it. So simple example also known about it. That means 1 by n be bounded. Okay, some sequence bounded. That means n is unbounded. Okay, in this way in is unbounded and I by n is bounded. Okay, We also discuss so many examples of bounded and unbounded sequence, and obviously known about it. One sequence is bounded when some xn less than m mod of xn less than m for all n belongs to n. Okay, then this sequence is called bounded. So we also discuss so many examples, okay, today. Now we also talk about more in later. So now we stop here, okay.